Alright, we're now going to move on to applications of differentiation, and our first one is going to be about the nature of our stationary points, okay, and it's going to be looking at what our gradient or our slope of our tangent is doing at all points along the curve. You will notice in the scanned copy of my notes that I've sketched this function as well. Unless the question actually requests you to sketch it, you don't need to sketch it. But please remember that when you are sketching, that you need x-intercepts, you need y-intercepts, you need any asymptotes, and you need to look at your behavior of the function as x approaches negative infinity and as x approaches positive infinity. Alright, so let's have a look at this question. So consider the function f of x equals e to the x, x take 2 all cubed. Calculate the derivative and hence determine the coordinates and nature of the stationary points. Alright, so let's have a first look at our function. We have that f of x equals e to the x, x take 2 cubed. And I can see that I've got two functions here multiplied by one another that are both containing x, and in practice what I also have is a function inside of my cubed, so I also have a chain rule with my product rule. Okay, so by product and chain rule, I'm going to let u equal e to the x and v equal x take 2 all cubed. U dashed will still just be e to the x, and v dashed will be 3 x take 2 squared. Okay, so f dashed of x will be u dashed v plus v dashed u, and that means I have e to the x, x take 2 cubed, plus 3e to the x, x take 2 squared. Okay, now because I'm wanting to find the coordinates and the nature of the stationary points, remember stationary points occur when f dashed of x equals 0. That means I'm going to need to take the time to factorize this. So I'm going to take out an e to the x and an x take 2 squared. What I'm left with then is an x take 2 plus 3, and that's e to the x, x take 2 squared, and x plus 1. And I'm going to communicate to my teacher that I know that stationary points occur when f dashed of x equals 0. So stationary points occur when f dashed of x equals 0. So now what I have is e to the x, x take 2 squared equals 0, and we can use our null factor law. And we have that e to the x equals 0, or x take 2 all squared equals 0, or x plus 1 equals 0. Remember, I can immediately discard e to x never will equal 0, so I discard that immediately. And here I have that x equals 2 or x equals negative 1. Okay, but now that's not a coordinate. Remember the question's saying determine the coordinates. That means I need an x value and a y value. Okay, so when x equals 2, I need f of 2, and that's going to be e squared 2 minus 2 cubed, and that's equal to 0. So my one coordinate of my first stationary point is going to be at 2, 0. And when x equals -1, I have f of -1, which is going to be e to the -1, -1 take 2 cubed, and that gives me 8 over, is it 8? No, 27. 27 over e. So that means that my second stationary point is at 27 over e. Negative 27 over e. Alright. Now, the next part of this is that I need to determine the nature. When they're asking about nature, they want to know whether these stationary points are local minimums or local maximums. And the way that I do that is to either use my second derivative test, or I can draw a little table. Now, if I have a look at my first derivative back here, okay, my heart drops because I can see that to do a second derivative of this, I'm going to have to do 3 chain rules. No, not 3 chain rules, 3 product rules. And that's going to take me a while. So in this case, drawing a table is going to be a whole lot easier. Okay? And the table needs to have values of x on either sides of my turning points. Okay, or my stationary points. So I see I have one over here at -1, and I have one at +2. So I'm going to pick a value less than -1, something between -1 and 2, and something greater than 2. Generally, I don't pick 0 because often in graphs there are various things happening around 0. So I'm going to draw my little table, and what I'm going to be looking at is what the derivative is doing at each of those points. Okay. Sorry to those of you that like all your lines to be absolutely perfect. So I'm going to have something to the left of -1. I'm going to pick -2. I'm going to pick my point -1. I'm then going to have something between -1 and 2, and I'm going to pick +1, not 0. Then 2, and then something after 2. You'll see in the textbook they pick values very close to the turning points. I find that makes the maths a whole lot harder. So this is my one turning point, and that's my other turning point. Alright, stationary point. Alright, let's have a look and see. We know that our derivative or our gradient is equal to 0 at that point, or those points. And so we can draw in little lines with 0 gradients there. Okay. Now, when x is equal to -2, my derivative, which is my function that I've underlined in orange over here, means I'm going to put -2 into that. So I've got e to the -2, -2 take 2 all squared, and -2 plus 1. So -2 take 2, -4 squared is 16 times -1, so that becomes -16 e to the -2. So that's -16 e to the -2. Alright. Now, I don't need to know exactly what that value is. I can see that -16 over e squared is going to be a negative gradient. Okay, it's a negative number. Alright, let's put 1 in. So now what we have is we have e to the 1, 1 take 2 all squared, so that's going to be 1, and then 1 plus 1 is 2. So what we've actually got there is 2e, and I don't need to know the exact value. I can see that that is a positive gradient. Alright? And similarly with 3, we get e cubed. 3 take 2 is 1 squared, and 3 plus 1 is 4. And so we have 4e cubed, and again, that is a positive gradient. Now the cool thing about drawing this little table is that we can actually follow our curve, and that gives us an idea of what we have. So what we have here is we have a minimum turning point at -1, and then what we have is a point of inflection on a rising curve happening at -1 and -27 over e. Alright? So therefore, -1 and -27 over e. I think I referenced the wrong one there with my little thing. At 2, we've got a point of inflection on a rising curve. So -1 and -27 over e is a local minimum, and 2, 0 is a point of inflection on a rising